For this lab, we were to observe the motion of a falling object and analyze it according to Newton's second law of motion, or the momentum principle, which is the final velocity is equal to the initial velocity plus the net forces divided by the mass of the object times delta t. And in this case, F net is not equal to 0 because there will be a weight force and a drag force on our objects. The weight force is equal to the mass of the object times the gravity of the Earth in this case, and the drag force is equal to a constant times the velocity, and in this case we are looking at the velocity squared to determine our drag force. I had my daughter hold a bowl and drop it. I recorded this video at 30 frames per second. I calibrated the distances by measuring the bricks at 0.055 meters, and I placed the origin of the coordinate system in the center of the bowl with the y-axis, positive y-axis facing up and the positive x-axis facing down. I tracked the object along the coordinate grid, which I did have to tilt just slightly to the left, and I received this graph from Tracker showing the motion of the ball in the negative y direction. You can see here that it's in the negative y direction, and it begins at the origin of 0. And this is the data I received, and the total running time was 0.433 seconds. I took this data to set up my model, and my initial conditions were that the mass of the ball was 6 grams, 0.006 kilograms, and the initial position of the ball was at 0, 0, 0, and the initial velocity was also 0, 0, 0, because I recorded just as she started dropping the ball. Delta t is very small at 0.001. Now, in order to set up my first model interaction, which was to be just the force of gravity on the ball, the weight force, I needed to set up a little more code, first specifying that gravity is 9.8, and that my vector is in the y direction, and I also need to set up the code to calculate the weight force and add that to the velocity, which is here as the mass of the ball times force of gravity in the negative y direction, and here is where F net would be equal to 0. This is a graph I found. This was my model, and this was my observation, which didn't match up well. So I went ahead and did the next observation to see what I could find. My next model was to add in the drag force, which you can see we still have the gravity force. We added in the B drag force constant, which I found to be for this model 0.00075. And here you can see the code, which is here the constant times the velocity squared, the constant times the velocity squared, and then the F net is equal to the weight force plus the drag force. And again, my graph did not exactly match up, so I went back to my observation, and I thought that it could be because the bowl was upside down when she dropped it. So I did my observations again and had my daughter turn the bowl the other way. I had pretty much the same conditions. I did have to tilt the coordinate axis a bit to match the falling of the bowl, and this time it was 0.5 seconds. But when I went back and I redid my calculations, this is my graph for the second video and Tracker, and again 0.5 seconds and a slightly different observation of the movement of the ball. I went ahead and I did the weight force graph again, this time with a time of 0.5 seconds, and I received a much closer calculation of the model versus the observed movement. I did the second one again, this time with a slightly different proportionality constant, because the drag force is different on the bowl when it's facing the other direction. Same code. And again, the graph was much better. It's still a little bit different here, but it's a much closer correlation. So my observation is that it was better to turn the bowl the other way because the drag forces are more evenly spread out over the bowl when it's facing up rather than when it's facing down, and the bowl would be tilting around and have much different much harder to calculate drag force according to my model. There were still some differences in this, in my observations versus the model here, but I think it's probably because the bowl was tilting around so much as it fell, and it didn't exactly match up with the y-coordinate axis the whole time. So that would account for the differences in the graphs. Also, my final observation was that using the drag force was a better predictor of the motion of the object than using just the weight force alone. The first what-if question asked if I examine the velocity versus time between both models, which predicts the terminal velocity. The terminal velocity is the constant speed that a freely falling object reaches when through the resistance of the medium to which it's falling. Both of these will reach a terminal velocity. It will just be a different terminal velocity because the drag force will slow the bowl down a bit than just the weight force alone. So both of them predict a terminal velocity. Also, what if, imagine the object was initially thrown down, and would the terminal velocity be different? Well, the terminal velocity of the object with the drag force would be the same eventually, but the initial but it would reach it faster. So to show this, I added in an initial velocity, ran the graph, and you can see that the model predicts that the object, if thrown down, would go down faster and reach the terminal velocity quicker than if it was just dropped. Thank you.